Welcome! In this session, we'll dive into the problem titled Reverse Only Letters. This is an interesting string manipulation challenge where we reverse the letters in a string while leaving all non-alphabetical characters in their original positions. Let's explore the problem and its solution step by step. In this problem, you're given a string S that contains a mix of letters and non-letter characters, and the task is to reverse the order of letters in the string while keeping non-letter characters in their original positions. This means that any punctuation, numbers, or symbols must stay where they are, and only the letters will be rearranged. The relative order of the letters in the reversed sequence must also be preserved. The input is a string made up of printable ASCII characters, and the output will be a string with the letters reversed and non-letters untouched. Let's look at an example. For the input S equals ABCD, the output is DCBA. Notice how the dash remains in its original position, while the letters A and D, and B and C, swap places to form the reverse sequence. Here's an explanation of the first example. The hyphen dash is a non-letter, so it stays in its position, while the letters on either side of it are reversed. Next, consider the second example, S equals ABCDFGHIJ. The output for this input is JIHGFEDCBA. As you can see, all the non-letter characters, which include 3 hyphens, remain in their original positions. The letters, however, are reversed in order. For example, A becomes J, B becomes I, C becomes H, and so on, while maintaining their original case. This means uppercase letters stay uppercase, and lowercase letters stay lowercase. Finally, let's look at the third example. For S equals test1 ing leet equals codeq. The output is keto1 ctelg equals nst. Here, the non-letter characters, including 1, dash, equals, and, remain untouched and stay in their original positions. Meanwhile, the letters in the string are reversed. For instance, T becomes Q, E becomes D, and so on. Moving on to the constraints, the string length will always be between 1 and 100 characters, and every character is a printable ASCII character. Letters are defined as AZ and AZ, while non-letters include anything outside these ranges, such as digits or punctuation. Some edge cases to keep in mind include strings with no letters, where the output will be identical to the input. Strings with only letters will result in a complete reversal of all their characters. Additionally, mixed-case letters must maintain their original case after reversing, and empty strings are not possible due to the constraints. To solve the reverse-only letters problem, the goal is to reverse only the alphabetical characters in the string while ensuring that non-alphabetical characters remain in their original positions. One simple approach we can consider is the brute force method, which relies on auxiliary data structures. The idea is to extract all the letters from the string and reverse them. Then, during a second pass through the string, we insert these reversed letters back into their original letter positions while leaving non-letters unchanged. This approach is straightforward and easy to implement. In terms of complexity, the time required is O(n), since we traverse the string twice, once to extract the letters and once to rebuild the string. However, the trade-off is the additional O(n) space for storing the letters separately, which might not be ideal in memory-constrained environments. The brute force approach, while intuitive, has a downside due to the extra space required for storing the extracted letters. To address this, we can explore the 2 pointers approach, which is more space efficient. Here, we use 2 pointers, one starting at the beginning of the string and the other at the end. The idea is to move these pointers toward each other, skipping non-letter characters, and swapping the letters they point to. This eliminates the need for extra storage, as the reversal happens directly within the string. The steps involve initializing the pointers, moving each to the next valid letter, and swapping those letters. This process continues until the 2 pointers meet or cross. The time complexity remains O(n), because each character is visited at most once, but the space complexity is reduced to O(1), making it a more efficient solution overall. Although the 2 pointers approach is optimized for space, it can be slightly more challenging to implement compared to brute force. Another alternative is the stack-based method, which combines simplicity with a structured way of reversing letters. In this approach, we push all the letters onto a stack, which automatically reverses their order due to its last in, first out behavior. Then, as we iterate through the string again, we replace the letter positions with the letters popped from the stack while appending non-letters directly to the result. This method is easier to grasp than the two-pointers approach, but it does require n additional space for the stack. Like the brute force method, the time complexity is n due to the two passes over the string. While it's a viable solution, the extra space for the stack makes it less optimal compared to the in-place two-pointers technique. The two-pointers approach emerges as the best solution because of its efficiency in both time and space. By focusing on swapping only the letters and skipping non-letters, this method minimizes unnecessary operations and avoids the overhead of additional data structures. The in-place nature of the solution ensures that space complexity is reduced to 1, which is a key advantage in scenarios where memory is constrained. A crucial insight here is that non-letters do not interfere with the swapping process, allowing the two-pointer technique to naturally handle the reversal while maintaining the string's original structure. While this approach may be slightly harder to implement than brute force, the significant space savings make it the most suitable choice. Overall, it strikes an excellent balance between efficiency and clarity, making it ideal for solving this problem effectively. To tackle the problem reverse only letters, we use a two-pointer approach, which is both efficient and straightforward. First, we initialize two pointers, one called left that begins at the start of the string and another called right that starts at the end. These pointers allow us to traverse and manipulate the string from both ends simultaneously. Since strings are immutable in many languages like Python, the next step is to convert the string into a list of characters. This conversion allows us to make in-place changes, such as swapping characters, without creating a new string every time. Once the setup is complete, the algorithm iterates through the string, continuing until the two pointers meet. During this iteration, we handle non-alphabetical characters by skipping them with the appropriate pointer adjustments. For example, if the character at the left pointer is not a letter, we simply move the left pointer forward to the next character. Similarly, if the character at the right pointer is not a letter, we move the right pointer backward. This ensures that both pointers are always pointing to valid letters when a swap is performed. Once both pointers are positioned at alphabetical characters, we swap the letters at their respective positions in the list. After swapping, the left pointer is increment, and the right pointer is decrement to continue processing the remaining characters. Once the iteration is complete and the pointers have crossed paths, the list will have all the letters reversed, while the non-alphabetical characters remain in their original positions. The final step is to convert the modified list of characters back into a string and return it. This step-by-step approach ensures that we achieve the desired result while maintaining efficiency. The two-pointer technique is particularly valuable here because it allows us to traverse the string in a single pass, giving the algorithm a time complexity of n, where n is the length of the string. This method also handles various edge cases effectively. For instance, strings with no letters, such as 1234, at hashtag, will remain unchanged because there are no alphabetical characters to reverse. Strings containing only letters, like ABCD, will be fully reversed, resulting in tkwa. For mixed strings, such as A1B2C, only the letters are reversed, yielding C1B2A. Additionally, by converting the string into a list, we perform in-place modifications, which eliminates the need for extra data structures to track indices or temporarily store characters. This reduces the algorithm's space complexity to n, which corresponds to the space required to store the input string as a list. The main data structures involved are the character list, which enables in-place modifications, and the two pointers, left and right, which facilitate efficient traversal and processing of the string from both ends. These choices minimize overhead while ensuring correctness. The code implementation begins by defining the function reverse-only letters, which takes the input string s. We first convert the string into a list of characters and initialize the left and right pointers. The main loop runs while left is less than right. Inside the loop, we first check if the character at the left pointer is non-alphabetical. If it is, we simply increment the left pointer to skip over it. Similarly, if the character at the right pointer is non-alphabetical, we decrement the right pointer. When both pointers are positioned at letters, we perform an in-place swap of the characters at the left and right positions. After swapping, the left pointer is increment, and the right pointer is decrement to continue processing the remaining characters. Once the loop exits, we convert the modified list back into a string using the join method and return it as the final result. This implementation is efficient and follows the algorithm's steps precisely. Key operations in the implementation include the use of the isalpha method to check whether a character is an alphabetical letter. This method ensures that only letters are considered for reversal, while all other characters remain in their original positions. The in-place swapping of letters within the list is another critical operation, as it eliminates the need for additional data structures like stacks or queues, thereby reducing memory usage. The loop's termination condition, which is when the left pointer is no longer less than the right pointer, guarantees that all pairs of letters have been processed correctly. The algorithm's time complexity is O(n), because each character in the string is processed at most once. The space complexity is O(n), due to the conversion of the string into a list, which is necessary for in-place modifications. These efficiency considerations make the solution well suited for handling strings of varying lengths and compositions. The algorithm also handles a variety of edge cases gracefully. For example, an empty string, represented as an empty set of quotes, will return an empty string as the output. Strings with no letters, such as 123 at hashtag, will remain unchanged because there are no alphabetical characters to reverse. Strings containing only letters, like ABCD, will be fully reversed, resulting in TQA. For mixed strings, such as ABCDFGHIJ, the algorithm will reverse only the letters, yielding JIHGFEDCBA. These examples demonstrate the robustness of the solution, as it consistently produces the correct output regardless of the input structure or content. By addressing these edge cases, the algorithm ensures reliability and correctness across all possible inputs. This solution efficiently reverses the letters in the input string while preserving the positions of non-alphabetical characters. The function reverse-only-letters takes a string S as input and outputs the transformed string. The main idea is to use a two-pointer approach to perform the reversal in place. First, the input string is converted into a list of characters so that we can modify it. The two pointers, left and right, are initialized to the start and end of the list, respectively. These pointers will help identify positions where alphabetical characters need to be swapped. The first while loop runs as long as the left pointer is less than the right pointer. Inside this loop, the left pointer skips over non-alphabetical characters by checking chars, left.isalpha, and incrementing left until it points to an alphabetical character. Similarly, the right pointer decrements until it points to an alphabetical character. This ensures that only letters are considered for swapping. Once valid letters are found at both pointers, they are swapped using tuple unpacking, chars, left, chars, right, equals chars, right, chars, left. Then, both pointers are moved inward to continue the process. After the loop completes, the list of characters is converted back to a string using .join, chars, which is then returned as the final result. This algorithm has a time complexity of O(n), where n is the length of the input string. The space complexity is O(n), due to the conversion of the string to a list, which is necessary for in-place modifications. All edge cases, such as the presence of non-alphabetical characters or an empty string, are handled naturally by the logic, ensuring a robust and efficient solution. Here, we define a class called solution and implement the method reverse-only-letters. The goal of this method is to reverse only the letters in a given string while preserving the positions of non-letter characters. We start by converting the input string into a character array, which allows us to manipulate individual characters directly. Next, we initialize two pointers, left, starting at the beginning of the array, and right, starting at the end. These pointers will help us traverse the array from both ends simultaneously. Inside the while loop, we first move the left pointer forward until it points to a letter, skipping over non-letter characters. Similarly, we move the right pointer backward until it also points to a letter. Once both pointers are positioned at letters, we swap those letters. After the swap, we increment the left pointer and decrement the right pointer to continue checking the next pair of characters. This process ensures that only letters are reversed, while other characters remain in their original positions. After the while loop completes, all the letters in the string have been reversed, and the non-letter characters are untouched. Finally, we convert the modified character array back into a string using the new string, chars, constructor and return the result. This ensures that the changes we made to the character array are reflected in the final output string. The overall approach is efficient, as each character is processed at most once, resulting in a time complexity of O(n), where n is the length of the input string. This implementation is both straightforward and effective for solving the problem. To solve this problem, we start by converting the input string into a list of characters. This allows us to modify the string in place, which is more efficient. We then initialize 2 pointers, left at the beginning of the list and right at the end. These pointers will help us traverse the string from both ends. In the first iteration, we check the characters at these pointers. Since both are letters, we swap them and move the pointers inward. In the second iteration, we encounter a non-letter character at the left pointer, so we skip it by incrementing left. Afterward, both pointers reference letters again, so we swap their values and continue moving inward. In the third iteration, both pointers reference letters, so we swap their values. Then, the pointers move closer to the center. In the fourth iteration, the left pointer encounters a non-letter character. This is ignored by simply incrementing left, allowing us to focus only on the letters. Once left and right both reference letters again, we swap their values and continue the inward movement. By the fifth iteration, we have letters at both pointers once more, so we perform another swap. At this point, the left and right pointers meet at the same position, indicating that all letters have been reversed properly. When the left pointer becomes greater than or equal to the right pointer, we exit the loop. This means all swaps are complete, and the string is fully processed. We then convert the character list back to a string, which gives us the final result. For example, the input string ABCDFGHIJ is transformed into JIHGFEDCBA. Next, let's consider another example where the string contains additional non-letter characters such as numbers and symbols. Here, we still follow the same approach, initialize the pointers, skip non-letter characters, and swap letters as needed. In this second example, the process begins the same way. The string is converted into a character list, and the left and right pointers are initialized at the start and end of the list. As the pointers traverse the string, non-letter characters such as dash and equals are skipped entirely, while letters are swapped in place. After processing, the final result for this example is keto1 ctelg equals enst. In a shorter example, such as obcd, the same logic applies. Letters are swapped from the ends inward, while the dash character is ignored. This results in dcba. The key insight of this solution is that non-letter characters are ignored by the pointers, ensuring they remain in place. Only the letters are reversed, and this is achieved using efficient in-place swaps with the two-pointer technique. The time complexity is O(n), because each character is processed only once, making this approach both simple and optimal for this type of problem. To analyze the time complexity of our solution, we start by considering the initialization step. Converting the input string into a list, which we call chars, takes O(n) time because we process each character once. Then, we use a two-pointer approach to traverse the string. The while loop continues as long as the left pointer is less than the right pointer. In the worst case, each pointer traverses the entire string, resulting in O(n) iterations. Within each iteration, we perform constant time operations like checking if a character is a letter using the isalpha method, which runs in O(1), and swapping two characters, which is also O(1). Since these constant operations are performed at most O(n) times, the total cost of the pointer traversal is O(n). Finally, after processing the list, we reconstruct the output string using .join chars, which also takes O(n). Adding these steps together gives us a time complexity dominated by O(n). Now, summing up all the steps, the overall time complexity of the solution is O(n) for initialization, O(n) for the two-pointer traversal, and O(n) for string reconstruction. Combining these, the total time complexity is O(n). When analyzing space complexity, we see that converting the string to a list requires O(n) space to store the characters. The algorithm performs in-place modifications on this list, meaning no additional data structures are used during processing. However, when converting the list back into a string, we need another O(n) space for the output. Since both the list and the resulting string are proportional to the size of the input, the total space complexity is O(n). This makes the algorithm efficient in terms of both time and space usage. Next, let's examine how the algorithm performs in different scenarios. In the best case, if the input string consists entirely of non-letter characters, the two pointers simply traverse the string without performing any swaps. Here, the time complexity is still O(n), because the pointers must check all characters. In the average case, when the string contains a mix of letters and non-letters, the pointers skip over non-letters and occasionally swap letters, but the traversal still takes O(n) time. In the worst case, when the string is made up of only letters, every character is swapped once, and the time complexity remains O(n). Compared to a naive approach, which might involve creating a new string, reversing all letters, and reconstructing the result, the provided solution is more efficient. A naive method would require additional space for intermediate data and multiple passes over the string, leading to O(n) time and space complexity. By contrast, this algorithm optimizes the process with in-place operations. Finally, let's solidify the O(n) time complexity with a mathematical perspective. Each character in the string is evaluated at most once, either by the left pointer or the right pointer, and no character is revisited. The isalpha method, which checks if a character is a letter, is called at most O(n) times, and each call takes constant time. Therefore, the total computational cost scales linearly with the input size, confirming the O(n) time complexity. As for space complexity, the algorithm uses only O(n) additional space for the list representation of the input and the final output string. No extra data structures are introduced, and the modifications are performed directly on the list. Consequently, the space usage is proportional to the size of the input, resulting in an O(n) space complexity. This balance of time and space efficiency highlights the practicality of the approach for large inputs. Here are some common mistakes to avoid when solving the reverse-only letters problem. First, reversing all characters, including non-alphabetical ones, is a critical error because the problem explicitly states that only letters should be reversed. If you include non-alphabetical characters, the output won't align with the requirements. Next, modifying the input string directly is another mistake. This happens because strings in many programming languages, like Python and Java, are immutable, so attempting direct modification can result in runtime errors or inefficient solutions. Instead, consider using a list or string builder for manipulation. Another frequent pitfall is mishandling edge cases, like empty strings or single-character strings. These cases should return the input unchanged, and failing to handle them properly can introduce bugs. Finally, not using the two-pointer technique efficiently can lead to suboptimal solutions. For example, extracting all letters into a separate list, reversing them, and then reinserting them increases time and space complexity unnecessarily. The two-pointer approach is much more optimal. A common misuse is the incorrect application of the isalpha method. Misunderstanding how it works can lead to skipping valid letters, including Unicode characters, or mistakenly treating non-alphabetical characters as letters. It's crucial to understand this function to ensure proper identification of alphabetical characters. Now, let's look at some key insights from an interview perspective. This problem is often used to assess your ability to manipulate strings while adhering to constraints. It tests your handling of edge cases and your understanding of efficient algorithms like the two-pointer method. Efficiency is a major focus here. Interviewers typically expect an O(n) time and O(1) space solution. You should also be ready to explain how your solution handles edge cases, such as strings with no letters, strings with only letters, or those filled with special characters. Lastly, discussing trade-offs is another great way to showcase your thought process. For instance, you can highlight the balance between clarity in using additional data structures versus optimizing for memory usage. This problem has several related problems that are worth exploring to deepen your understanding. For instance, LeetCode 344, reverse string, is a simpler variation where all characters are reversed. Another example is LeetCode 345, reverse vowels of a string, which is similar but focuses on vowels instead of all letters, making it a great practice problem for the two-pointer technique. Additionally, LeetCode 125, valid palindrome, shares similarities since it involves skipping non-alphabetical characters while processing the string. Speaking of approaches, the two-pointer method is the most efficient way to solve this problem. Here, one pointer starts at the beginning of the string and the other at the end. The idea is to skip non-alphabetical characters and swap only letters. This approach runs in O(n) time with O(1) space, making it optimal. However, careful implementation is necessary to ensure that all edge cases are handled correctly. Another approach to consider is the extract and reconstruct method. With this technique, you first extract all the letters, reverse them, and then reinsert them into their original positions within the string. While this method also runs in O(n) time, it uses additional memory, making its space complexity O(n). The trade-off here is that it's easier to implement, but it's less memory efficient. Lastly, there's the recursive approach, which involves processing the string recursively and reversing letters during the backtracking phase. This method has a time complexity of O(n), but comes with an O(n) space complexity due to the recursion stack. While it's conceptually interesting and can demonstrate your understanding of recursion, it's not ideal for large inputs because it may lead to stack overflow in certain languages. Each of these approaches has its strengths and weaknesses, so it's important to choose the one that best fits the constraints and requirements of the problem at hand. Great job! We've successfully solved the reverse-only letters problem using an efficient two-pointer technique. Remember, these techniques are invaluable for string manipulation challenges. Thank you for watching, and I hope this session was helpful. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!